So today let's examine these two donated USB chargers. Are they any good, or am I going to add them to my collection of electrocution house burners? This one says original and it has 4 USB ports on it. And this one has 2 ports and says power quick charge. Let's take a look at this one first. Both have a European plug. This one seems to have some indication LED or LEDs. These 2 ports, 2.1 amp, 3 amps, quick charging, and the marking, some model number, universal mains input, output 5 volts, 2.1 amps for one output, and the other output is the quick charging one, 5 volts 3 amps, 9 volts 2 amps, or 12 volts 1.5 amps, and the total power 28 watts. We're definitely going to try this, and today let's do it the other way. Let's take a look inside of it first and then let's test it. Somebody probably already took a peek inside of it, so it's going to be easier to open, I guess. This comes off and here are the internals, the ports. Does it come out? And it has 2 power supplies in it. 2 transformers, 2 primary smoothing capacitors, 2 auxiliary capacitors on the primary side, 2 small capacitors for interference or for a snubber, the input of mains with some fusible resistor maybe, 1 optocoupler, the output ports and smoothing capacitors, some interference capacitor probably here, and the other side of it, some SMD components, the bridge rectifier, 2 switching chips on the primary side and 2 sets of components, some snubber diodes, auxiliary rectifying diodes probably, or just one here basically, some startup resistors, current sensing resistor probably, and the secondary side seem to have some synchronous rectifier chips, I guess. Here's some voltage reference, some communication chip, and this side is the power supply which can change its output voltage, and it also has an optocoupler, and the other one has no optocoupler and no communication chip on the secondary side, because it's just 5 volts. The green transformer is in the one that's just 5 volts, and it also has just a 10 volt capacitor at the output. The other one has 16 volt capacitor here, so it can actually switch the voltage up to 12 volts. Has an optocoupler, this yellow transformer, and now of course let's take a look at the safety. The isolation is here. It's sort of kind of, even though it could be better, there is some capacitor between the primary and secondary side. Is it a safety capacitor? Of course it's not. It's just an ordinary 2.2 nanofarad 1 kilovolt capacitor, but in this position between the primary and secondary side it should be a safety class Y1 capacitor, because it's the only thing isolating the user from mains. And only one output seems to have this interference suppression capacitor, the other one doesn't have it, and these two are at the part of the snubber networks, not for interference suppression, and there is no other interference suppression component in it. And of course the markings of the components. Here's the primary side of the 5 volt only power supply, and its synchronous rectifier. The primary chip of the quick charging part of it has no marking whatsoever. Here's its synchronous rectifier, and here's probably the communication chip, the tiny one, negotiating the output voltage with the load. And of course the tiny 3-pin package here is a 431 voltage reference. And the isolation distance between the primary and secondary side is about 2 millimeters here. I have seen much worse, but this is probably still not up to a European standard. And there seems to be a straight connection between the negative rails of the 2 outputs. But now it goes back into the box and let's do the loading test. Let's plug it in. The LED lights up and let's give it some testers. This one actually, if I put this one here, this one is going to cover it. So let's plug it into this, which I might need anyway because I need to switch it to a higher voltage than 5 volts. Let's also check the voltages can be switched first. 5, 9, 12. Let's leave it at 9. And this one, it's 5 only. This one is going to get this test lowered and load it at 2 amps. And the other output is going to get my DIY test lowered, which goes up to 4 amps, 4.25. And here is the circuitry in it. And the USB port goes into this meter, increasing the load up to 2 amps. And now it's 2 times 9 is 18 watts, plus 2 times 5 is 10 watts, in total 28 watts, the full power. Let's leave it baking at full load for a couple hours. He came back to it after about 15 minutes, and the box of the charger is already untouchably hot. I can't keep my finger on it for more than a couple seconds, and it's cycling on and off. It seems the overtemperature protection in the quick charging section of it is thermally cycling. It's reaching the maximum temperature, shutting down and restarting. So hell no, it can't handle 28 watts. Both of them are now thermally cycling. This one is now cycling even at 1.6 amps. Both cycling even at a reduced current. It ran for about 3 hours just below the threshold for cycling and no explosion. That's the temperature of the housing, about 87 degrees Celsius. From below over 90, 92. Amazing. Let's quickly unplug it and open it and see the temperature on the board. And here is the board. 117 degrees Celsius here. The chip is 107, 118, 120 degrees Celsius, almost electrolytic capacitor, nice. The transformer winding, 130 degrees Celsius. And of course it's not easy to get accurate temperature readings because when you unplug it, disconnect everything, take it from the box and then look at it, it's already cooling down quickly. Now I run it at the full current and let's take a look at it when it's open, while it's still running. And now a bit more realistic readings. The chip of the 5 volt only section is 186 degrees Celsius. Bloody hell! Now it actually cycles and drops a bit and goes back up. And the synchronous rectifier of it is 130 something. And the adjustable power supply is 130 degrees Celsius and its synchronous rectifier 110 degrees Celsius. And the transformer winding almost 140 degrees Celsius, and this is still underestimating because it's not in the box. It's in free air with way more convection cooling. It can't be complete without opening the transformers, and they're not identical, so I have to open both. It broke in the process, but who cares when you're removing it just to dismember it anyway. And this is the 5 volt only section. I heated it and the ferrite core opened. It has an air gap because it's a flyback switching power supply. And this one is the one with the auxiliary winding, which seems to be the first winding, and it seems to have enough insulation under it. And it's far from the gap, 10, 11, 12 turns. And it seems like a good enough insulation under it. No gaps or holes. And here's the secondary under it probably. 1 layer. 2 layers, and here's the secondary. It's made of multiple wires twisted in a parallel because it's a high current one, and this is better than just one thick wire because it reduces the skin effect. It keeps some distance from the gap in the tape and some distance from the ends of the primary here. It's about 1 millimeter, but it's not touching. Of course this could be much better but also much worse. I have seen transformers with no insulation, where all the windings are just sitting one on another. But of course the best ones have a thick insulated or triple insulated secondary with a very thick safety insulation instead of just the normal lacquer. 1, 2, 3, 4, 5. And here's the insulation. Seems sort of good. No gaps in it or holes. 1 layer, 2 layers. And the primary, which is 1, 2, 3, 4, 75. Now the quick charging transformer. At least one taken out without disintegrating it, isn't it nice? Let's open it. The melted hairdryer again. The core is out, and this one doesn't have an auxiliary winding. It has 2 pins for the secondary and 2 pins for the primary and 1 pin unused, and 1 pin as a connection between the halves of the primary, I guess. So is it a split primary construction? Let's see. The insulation on top. Here seems to be the first section of the primary. So let's remove it and let's see. And also the primary doesn't go all the way to the ends of the secondary here. And it goes to the center point. making no connection with anything. One layer of insulation, 2 layers, and the secondary, this time 6 turns instead of 5. 1, 2, 3, 4, 5, 6. The insulation under it, no gaps, but the secondary was very close to these ends of the primary, which is not really the safest. 1 layer, 2 layers of insulation, and the rest of the primary. This section is 75, and the first section was 15, so in total it's 90 turns on the primary. Okay, so let's sum it up. The insulation in the transformers could be much better but also much worse. The 2mm isolation distance on the board could be much better but also much worse. And the 1 kV non-safety capacitor between the primary and secondary side isn't up to a safety standard. There is virtually no interference suppression. It can't really supply the power it claims. And it's massively overheating with one chip over 180 degrees Celsius. The maximum operating temperature of silicon is 150 degrees Celsius. But for longevity and reliability, the temperature should be even lower than this. And the 105 degrees Celsius electrolytic capacitors are getting completely baked. So the conclusion is dodgy. Now the other one, it says original on it, and it has 4 ports here, 3.1 amps, it says on the first 3, and the last one says some quick charging symbol, it seems, and here it says fast charging, some model number, universal minus input, output 5 volts, 3.1 amps. Is it not other voltages than 5 volts? I guess it should be when it says fast charging and this symbol on this port. If it cannot supply more than 5 volts, why these 3 ports are different than this one? How is this port with the quick charging symbol any faster than this? Let's open it and see if it contains 1 power supply or 2 power supplies, and if the quick charging port is connected any different. It opens. It was easy, and there is just 1 power supply with just 1 transformer, a discrete diode here, no synchronous rectifier. That's going to be interesting. At 3.1 amps this diode has to get bloody hot. Is this tiny thing the only secondary capacitor? Bloody hell. And 1 chip here, the bridge rectifier, couple of resistors and diodes, and that's it. And it seems all 4 ports are connected in parallel, so there is absolutely no difference between the 3 ones saying 3.1 amp and this quick charging symbol port. The isolation distance is again about 2 millimeters. Here is the marking of the primary chip. And the soldering quality is amazing. Look at how this SMD resistor is soldered. It's the series resistor of the LED in it. Also a solder joint with a hole here. Here is the LED, and all 4 ports have the data pins connected with each other and not even going to the board. And there is no optocoupler and no secondary side chip anywhere, so it can't really change its output voltage. Here's the bridge rectifier, some snap network components, I guess the current sensing resistor, some resistive divider in the voltage sensing, the diode rectifying the auxiliary winding, some startup resistor, and that's it. And here is the capacitor in the snubber network, the small blue one here. The inrush resistor may be fusible, and the small capacitor rectifying the auxiliary winding, or smoothing it. And here is the capacitor between the primary and secondary side, which is again not a safety capacitor. The board says CY, a Y-class capacitor, but it's not. I have never seen this between the primary and secondary side. Here is the diode, which is a Schottky. But of course, if you want to rectify a high current using a component with no heatsink and in a small confined space, you want to use a synchronous rectifier, which drops less voltage than a Schottky and dissipates less power than a Schottky. And also this funny small capacitor. Take a look at the huge footprint under it and how tiny the capacitor is. It's 300 micro, 6.8 volts. It might be some polymer capacitor with a low ESR. But still 300 micro for 3.1 amps seems a low smoothing capacitance. There's some type number on the board. I guess the hottest component is probably going to be this diode. Maybe it's not going to be the chip. It might be running at 150, maybe 200 degrees Celsius. Of course, given the power supply can actually supply the 3.1 amps it claims. So let's bake it. Let's put it back into the box and try to load it. Let's plug it in, and there is an LED, but I don't see any place where the light will come out. There is a blue LED in it, with no hole for it. But anyway, would expect it to make any sense. And increasing the load. 1 amp, 1.5. At 1.9 amps, the voltage suddenly goes down. 1.8 amps, 5.3 volts. 1.9 amps, 4.7 volts. 4.6 and shutting down. It can't even make 2 amps. So it's not going to be such a Schottky diode grilling party. Nothing's exploding after 3 hours and it's not even that hot, it's just warm. But of course this one supplies just 10 watts. Just 55 degrees Celsius. At the bottom 60 degrees Celsius. I very quickly unplugged it, opened it. Here's the temperature. 93 about. The hottest spot 81 degrees, the chip. The hottest thing is probably the diode and the transformer, 90 something degrees Celsius. Now let's try to look at it while it's running. And the diode is 106 degrees Celsius. The transformer winding about 90 something. And the switching chip is 95 degrees Celsius. So the hottest component is the diode, just slightly over 100 degrees Celsius. Boring. I've made an observation hole in it and covered it with a tape. And looking through the hole, I can see the shape of the diode. The tape seems to be partially transparent for infrared, but not fully. It skews the measurement. When I remove the tape, the reading is quite different. 110 degrees Celsius. And this is probably the most realistic reading so far. And you might be asking what the ripple at the output with such a small secondary capacitor. At this current, the ripple is this. This is AC only, the output, about 680 millivolts peak-to-peak ripple. Nice! And the operating frequency is about 60 to 70 kHz. And turning the loading current down. And I guess now the transformer core should open without even heating it using my melted hair dryer. Because it's about 90 degrees Celsius or almost 100. Of course. Unfortunately it still does not self-desolder, but it was at least easier when it was preheated. Here's the insulation on top. Let's remove it and see the windings. 2 layers of this and then the auxiliary. And of course the auxiliary winding is on the primary side. And I don't like how close it is to the secondary ends. There is almost no insulation and insulation distance, especially given how this insulation tape is pre-molten here. It's probably similar. Remember, this wire is connected to the user potentially because it's connected to the negative of the USB port and the shielding shell. So it goes to the exposed metal on the connector, or potentially to the metal body of the phone or other device. And this winding is connected to the mains. There is just about no insulation. There is a lacquer on the windings, but it's just 0.00 something millimeters thick and never meant as a safety insulation. And of course, just for scale, these are millimeters. What's isolating it? Almost nothing. But let's remove the auxiliary 1, 2, 11, 12. The insulation under it is definitely questionable. Here it looks a bit molten. Here as well. Now let's remove the tape, which breaks. It actually broke here in the molten area. It's 2 layers. There's 3. Here's the secondary, which is made of 2 parallel sections. 5 turns of 2 parallel wires. And here's the insulation under it. But the worst thing is that the secondary was sitting on the exposed ends of the primary here. They're not covered with anything. This is more or less isolated just by the lacquer on the wire. This is before removing the secondary. It was sitting on the ends of the primary. Removing the insulation and here's the primary. The insulation seems a bit molten, I guess. Let's take a closer look at the capacitor between the primary and the secondary side. This green rectangle here. 2J, 222J. Let's just Google it. It's on eBay, Amazon, Alibaba, AliExpress. $1.71 for 100 pieces. So this 1.7 cent capacitor isolates you from a minus. And it's rated for just 630 volts. One terminal of the capacitor is on the minus side, and the other one goes to the metal shells and negative terminals of the USB ports. And the proper capacitor for this application is a class Y1 capacitor, which I believe is tested at 8 kilovolts. Very often they use a 1 kilovolt capacitor only, which is already quite horrible, but in this case they went even farther and they used a 630 volt only capacitor here. This is probably the lowest voltage rated capacitor between the primary and secondary side of a switching power supply I've ever seen. So let's sum it up. This one has most of the problems of the previous one, but on top of it, the previous one at least was able to supply its rated current for several minutes. This one can't supply it at all. The previous one had at least a millimeter between the windings. This one had the secondary sitting on the ends of the primary. And the voltage rating of the capacitor, which is critical for safety, is even lower here. So the conclusion is super dodgy. So that's it. Don't use questionable chargers unless you like electric shocks and fires. And if you like my videos, please consider supporting this channel on Patreon, using the thanks button and subscribing, because this is how you keep this crazy channel running.